January 4th, 2014, 7:29 p.m. It's been a long day, but the chili's good. So that was my dramatic play for the day. If you didn't notice, I was pretending to be a ship's captain, journaling in my logbook, or logging in my journal book, and that was that. But this is the problem, Mr. Reed. We're here to do math, not talk about how much of a dork you are. So let's look at problem number 2. Again, no calculator on this problem. We want to sketch each graph and state the domain and range of each of the functions. So let's go ahead and take a look at number 2, part A. We have the function y equals 2 times the absolute value of x plus 3 over x plus 3, and then minus 1. So the mother function should be standing out to you. You should recognize those fancy absolute value, and you should notice that we have an x in the denominator as well with the same translation of plus 3. So this is our mother function, absolute value of x over x. And if you remember, that's the graph that looks like that. 2 lines with a hole in the middle. Normally, that hole is on the x value of 0 and the y value of 1 and negative 1. Whoa, why did I write a 2? That's weird. Negative 1. But let's take a look at what these transformations are. First off, Mr. Reed, why do we have a hole? That's a very good question. Well, there's this thing called fractions, and there's this thing called math, and math decided that when you have a fraction, 0 is not allowed to go in the denominator. So I don't care what your numerator is, if your denominator equals 0, then you are out of luck, because math says you cannot divide by 0. And we must oblige math, because math is, pretty awesome. Anyways, let's look at these transformations. First off, I already mentioned it. Look at how we have a plus 3 in the numerator and the denominator. That is actually how you do a horizontal translation for an absolute value function. If you don't have the same transformation in the numerator and the absolute value and in the denominator, things get crazy and you get graphs that look like that's not actually what they look like, but they get messed up. It'd be funny if I just stopped the video there. I won't, though. I'll keep going. The other transformation we have is a minus 1. And notice that is at the end. It is an after-the-fact thingy. It's like the last thing you're going to do to this function is subtract 1 from it if you are like me and follow the order of operations. So that's just going to move our graph down 1. And that plus 3 is going to move it left 3. What about that 2? What is that stinky little 2 going to do? Well, that's kind of like as if it weren't there, but we're like there. That's multiplying that entire fraction there by 2. If you think about the x squared graph, if you multiply the x squared graph by 2, it stretches it. It makes it grow more quickly. This is kind of similar, except that I wouldn't really say it grows more quickly, but it definitely stretches it. So if we draw ourselves some lovely axes there, and I'll go blue for my graph, well, instead of having the y values occur at 1 and negative 1, they will occur at 2 and negative 2. Maybe that's why I started writing the 2 before. My brain was just jumping to it. I don't know. But anyway, that's happening because of that 2. It's multiplying those y values that should have been. So it's going to stretch it. And instead of having a gap of 1 there, it's going to have a gap of, instead of having a gap of 2, it's going to have a gap of 4. And when I say gap, I'm talking about the distance between those two holy things. And I don't mean holy, I mean hole-having things. So one more thing we need to think about, that minus 1 is going to affect where these two legs are. So they're not going to be at 2 and negative 2 like that. They're going to be shifted down, so they're going to be at 1 and negative 3. So let's piece all this together, because holy moly, Mr. Reed, that was a lot of stuff. Did you hear my dog bark? She just barked. So we're going to shift it to the left, 1, 2, 3. One of our y values is going to be at positive 1 right there. Whoa, that's not a circle. That's a circle. One of our y values is going to be at negative 3 right there. And it is going to shoot off to the right forever, constantly. And it's going to shoot off to the left forever, constantly. And there's a hole right there, which means like, it's all like gappy right there. And if I tried to touch my graph there, it would just like disappear and my hand would go into nothingness. It wouldn't exist. I certainly wouldn't touch my graph because it does not exist at the x value of negative 3. But why, Mr. Reed? Because what did we say? You cannot divide by 0, and that denominator is x plus 3. So if I substitute in negative 3 for x, I'm going to get negative 3 plus 3, which is 0, and you cannot divide by 0. Get it through your head. Can't do it. So that's that, but we should probably list the domain and range because Mr. Reed asked us to. So domain of this function. I'm not going to do it in fancy notation for the purposes of this. Look at my notes if you want to, or just do it yourself because you know how to do it now, or you don't and you don't want to know how to do it. So instead of doing fancy notation, let's just state the most important part about it. X is not equal to negative 3. If you do that, I'll accept it, and apparently AP will too. So now let's talk about our range. Our range is just two numbers. So the numbers, I'm going to put negative 3 first because it's a smaller number than my other number, which is 1. And notice that because these are curly braces instead of parentheses, I'm not talking about an interval. I'm talking specifically about the numbers negative 3 and 1, positive 1. So remember, domain is talking about what are the possible x values I can plug into my function, or another way to think about it is what x values can I not plug in. Sometimes it's easier to say one or the other. With the case of the range, when we're talking about all the possible outputs, the y values, in this case it was easier to say the y values that did happen, negative 3 and positive 1. So there you go. Holy mouthload, that was a lot of talking. So let's look at number 2, part B. Looking at this, we've got one of those square roots with some weird subtraction and squared stuff in there. So you're probably thinking at this point that it's either the semicircle or the semi-hyperbola. They're both very similar. They both have those endpoints. Oh, that looks like a little like character, almost like a face, like huh. But I probably shouldn't do that. We should focus. They're both going to have those endpoints, and those endpoints are occurring at the square root of that number. So they are occurring at 2 and negative 2. But again, I don't know which one is which at this point. So let's do a little math. The basic functions here are these two. If we look at this, we've got r squared minus x squared square root. That's the mother function we're dealing with here. So that's equal to y. Let's square both sides, and then we're going to get r squared minus x squared equals y squared. And if you remember your conic sections from last year, r squared equals y squared plus x squared is the equation of a circle. So we are in fact dealing with a semicircle, not the semi-hyperbola. So let's see what we can do with that. We already said the endpoints are going to occur at negative 2 and positive 2. That y value right there is also actually going to be 2, but we have a translation 2 units to the left, and we also have a vertical reflection. So instead of being a frowny semicircle, it's going to be a smiley semicircle. So let's draw our axes. It's going to shift it left 1, 2. So it's going to be centered there. It's not going to have a value there, but if you think about the center of the graph right there, that's where that's going to occur. And since the radius is 2, from this point that we just put there, it's going to go 2 to the right, so it's going to have an endpoint there, and it's going to go 2 to the left, so it's going to have an endpoint there. And then it's going to go 2, ooh, wait, Mr. Reed almost made a mistake again. Not up, but down because of that reflection. So it goes down here. And so go to your center and go down to that Y value. And then draw in your happy face. Boom. And that's cool. Notice I'm not putting arrows on the end of my graph because for this to be a function, it actually needs to stop right there and have those endpoints. So if we talk about the domain, we're talking about this interval here of x values that goes from -4 to 0. So I'm going to write that as bracket -4, comma, 0, close bracket. And I'm using brackets, not parentheses, because brackets imply that those values, -4 and 0, are included. Parentheses means they are not included. So let's do our range. Again, brackets, it's going this time from -2 up to 0. I know it's tempting to do 0, comma, -2, but try to put the smaller number first. And that's that one. Cool. Hopefully I didn't make any mistakes. Let's go to part C. So, 2/3 graph is the 2-bird graph, but it's actually only one bird. This is our mother function that looks like that. It's kind of like a square, or I'm sorry, like a absolute value graph, except it's not straight. It's curvy, exaggeratedly so, like that. And they look like birds, and they're pretty, so that's why we call it the bird graph. But anyways, the bird graph is supposed to occur right like that, with its little bird beak tail thingy right at the origin, and then it goes up and to the left forever and up and to the right forever. It doesn't go down, that's for sure, because of that squared bit right there. So let's look at our translations. X plus 3 means go to the left 3. Plus 4 on the outside, again, it's kind of like an afterthought. That's going to move it up 4. So those are my two translations. Let's draw some axes. Let's move that vertex point, the beak of our bird graph, the feet of our bird graph. I know those are like totally different things, but you know, you could interpret it however you want to. It kind of looks like a beak when you do two things like that. So don't judge me. Ooh, that also kind of just looks like an angry bird that's about to like eat you. Oh, and apparently it has a mustache. So anyways, left 3 means 1, 2, 3. Up 4 means 1, 2, 3, 4. So this is that point right there, and it's gonna go caw, caw. Domain is gonna be all real numbers. The range is going to be all real numbers, y values that are greater than or equal to 4. Because of that 4 right there. Boom, done with that. Last one, y equals 4 over x plus 1 minus 2. A lot of you in class today were like, oh my goodness gracious, Mr. Reed, I can't do this problem because there's a 4 right there. Well, how about this? Let's do like what we did with that absolute value graph. Let's pretend it doesn't exist for the moment. Let's pretend there's a 1 there. At the end, we can then be like, oh yeah, I need to multiply that by 4. But for now, let's not even write that there. Let's pretend that this said 1. Well, if it said 1, then, oh, okay, I can do that. This is the mother function 1 over x, which looks like this guy. Lair actually figured out how to do this with his body today, so you should totally ask him to do it sometime. It's pretty awesome. I couldn't figure out how to do it, but the Lair did, so that happened. Let's actually, I lied, let's actually do talk about that 4 right now. Let's not pretend like it doesn't exist, because it does exist, so that's rude of us to ignore it. Normally, this graph has these two key points on there. An x value of 1 with a y value of 1, and a x value of -1 with a y value of -1. That 4 is going to stretch this graph out, so instead of those points occurring at positive and negative 1s, you're going to get this situation where The x value is the same, so this special thing is still going to happen at x equals 1, but instead of y equaling 1, y is going to equal 4, and instead of y equaling negative 1 when x is 1, y is going to equal negative 4. But other than that, it still mostly looks the same. It's still going to have horizontal asymptote at y equals 0, but in this case, not so much because we have other transformations. But, if I'm doing that thing, that is what 4 over x would look like. So it's really not, anything to be scared of. All it does is move those points up to positive and negative 4. I mean, it moves every single other point as well. These points are just easily identifiable, so I use them. But every single point is going to get multiplied by 4. That's all it does. It's a stretch. It's a stretch factor. It's a dilation. Let's keep going. Holy crap, Mr. Reed, this is 16 minutes already, so finish it up. So let's draw, whoa, sorry about that. Let's draw our axes, because I'm tired of listening to Mr. Reed battle on. But you have the whole weekend to do this, so you ain't got no excuse. Ain't is not a word. Mr. Reed doesn't know English. Let's do this now. So, we already talked about what that 4 does, but let's talk about that plus 1. Well, that's going to move it to the left 1. And that minus 2 is going to shift it down 2. So let's think about those points. They're going to go down 2, each of them. So when we go 1 to the right of our graph, the center of our graph, the axis of symmetry of our graph, aka I'm saying it's happening at the y value of 0 now instead of 1 because we shifted to the left. But we need to go to 4, but we got to subtract 2 from it. So let's go to 1, 2. I'm going to get a point happening right there. And instead of negative 4, we're going to go to negative 6. So 1, 2, 3, 4, 5, 6. So that's happening right there. That's an absolute lie. That's not happening right there. That is, whoa, I lied the other one too. Okay, whoa, Mr. Reed, you're crazy. Do you see what I did wrong? Take a moment and look. I'm going to change colors. So this point should be there. And this point should be, whoa, that was weird. This point should be there because I'm actually going to have a vertical asymptote running down the middle. Normally, it runs down the line x equals 0, but since we are shifting it to the left, the asymptote gets shifted to the left as well. And speaking of shifting asymptotes, that negative 2 is going to shift the normal asymptote that happens when y equals 0. It's going to shift that down too. So instead of happening at y equals 0, it's going to happen at y equals negative 2. So it's easier to draw in my graph now that I've drawn those asymptotes. And let's do it. I'll do it in green for some reason. So, there's one branch. And quick reminder, an asymptote means your graph will never cross that line. Let's draw another one. Whoa, you missed it, Mr. Reed. I saved you 20 seconds there after wasting so much of your time. But there you go. They look pretty nice. Domain of this function is going to be every x value except that asymptote, which is at x equals negative 1. So I'm going to say x is not equal to negative 1. And my range will occur everywhere except for that horizontal asymptote, which is all y values that are not equal to negative 2. Sweet. You're welcome. That was 19 minutes of me. I'm so sorry.